algebraic topology. Oh, sorry. Invariants of spatial graphs and associated subgraphs. Thank you.
Okay, thank you very much for very kind introduction, and big thanks to organizer for this very nice conference in serious hospitality, and especially best regards and best wishes to Viktor Matveyevich. And I will talk mostly about slow-dimensional topology, because I remember that we spent with Viktor Matveyevich many times in discussion when we met in Eberwolfach. It was many years ago. It was two conferences. One conference was about algebraic topology, and it was parallel conference about knot theory and low-dimensional topology. So we met and we discussed it, work in this area. So after that, we organized many conferences in China on common subject, algebraic topology and low-dimensional topology. So I suppose the subject will be also close to many participants. Okay, let me try to. Okay, I want to tell you about some motivation why we study the spatial graphs, and so I want to present you some results about spatial graphs, and a few modern results will be in the last section. I present some relation between Yamada polynomial, which is polynomial for spatial graphs, and the famous Jones polynomial for nodes. It will be my aim. So motivation is kind of a motivation for our ministry of science, because they always ask us about applications, and I would like to tell you about two possible applications on spatial graphs. There is a very nice project called Node Proteins. It's an international project, and here head is Janusz Olkowski. The people study proteins. There is a very big protein database, data bank, and also they are presented not just proteins, but also noted structures related to these proteins. And you can see here some proteins and corresponding nodes. So you have carbon and azote, and when you close these ends, you'll get usual nodes. And there is a very nice site. You can find a lot of information in this site, which is called NodeProt. And also you can calculate many invariants, many topological invariants, because you see there is Millet, one of people who participated in this project, very famous expert in the node theory. And you can consider not just nodes and links, but also you can consider some graphs. For example, when it was a COVID situation, so there was many discussion about possible vaccine, and there were some papers about Japanese horse crab, about the collagen of this crab. It's a picture of the crab, and this structure from NodeProt. It looks like a knot in the space, but if you add some covalent bonds, you'll get a graph. So you can consider this graph, which characterizes chemical structure, and also you want to distinguish this graph among others, so you need some invariants. And so this kind of possible application. And another application is more fresh, much more fresh. It's paper published in Journal of Mathematical Design just in this month. And I got this information about this paper just because they cited our papers about noted graphs. So this is about design, and in this paper, people consider it a three-dimensional topology to present optimal engineering system and to modulate this spatial graph. So it's kind of automotive full cell system. There are a lot of details of virtual, and what is important, you have a lot of connections between different parts, and it is everything in three-dimensional space, and your problem to organize it is the best way to minimize crossing or something, to minimize length and so on. And very surprising is this paper, they discuss it very nice topology. So they consider the model of this system as a special graphs. There is 14 vertices which correspond to engineering paths, and you see two embeddings of such graphs which present different structures and people consider these models. Also, they calculated some invariants about which I will talk a little bit later. So it's very fresh. It's published just in this month. Okay, and let me go to mathematics and go to beginning of the special graph theory. And in my opinion, it started from very famous example, but the most simple example. Let us consider graph, which very elementary from the graph theory point of view, only two vertices and only three edges. So you have two vertices connected by three edges. So since it's a look at the letter theta, it's called a theta graph. It's only this meaning. So it's theta graph, and we consider embedding in three-dimensional space, and we always consider smooth embedding. So we can consider something in the space, which we call the spatial graphs. And the theory of spatial graph is a very natural generalization of theory of nodes, because if you consider cycle in your graph, in the embedding, you will get a node. So for example, here in this simple graph, you have three cycles, which presented in the picture. So you'll get three nodes. And these nodes, call it consistent nodes for this special graph. And there is a very nice result obtained by Kate Walcott about these sub-nodes, also this consistent graph. So she proved that if you give any three nodes, so they can be realized as a consistent nodes in the theta graph. So you have very simple graph, but any cycles can be embedded as a node which you want. It can be very complicated, and moreover, these nodes don't determine special graph uniquely. There is a lot of examples where you have the same nodes but different graphs. And it was published in her thesis, and it's not easy to find the original paper, but many people cited this. It's very famous. And similar to nodes, we can draw special graphs. These pictures for theta graphs. So it's a very simple picture. Theta 1 and the next are trefoil with some bridges, figure 8 node with some bridges, and so on. So people started to tabulate it. Similar people did in 19th century for nodes, and it was started by Simon, and after that Rizal did it up to 7 crossings. It was unpublished, and he didn't prove that his list is complete. And at the end of the story, in 2009, Morici enumerated theta curves up to 7 crossings, and he proved that his list is complete up to this number of crossings. So we have many such examples, and we can, similar to the node theory, we can start diagrams. With diagrams, and we are considering not just theta graphs, but we can consider arbitrary graph. So we consider only finite graphs, so finite number of vertices, finite number of edges, and we consider embedding in the space. We call it spatial embedding. And of course, if you have a cycle, so you'll get a node in the space. If you have a couple of disjoint cycles, you get two-component link, and so on and so on. So you can discuss such kind of examples. And similar to the node theory, we consider special graphs up to equivalence, and equivalence is ambient isotopy. Usually ambient isotopy, but sometimes more careful equivalence. I will tell you about it later. So this is the object, and similar to node theory, we have very nice result, which generalized famous Erdemeister theorem for nodes. So I recall in 1927, Kurt Erdemeister proved a very nice theorem about diagrams of nodes. So you can consider nodes in the space, and you can consider the diagrams. So projection where we show which arc is up, which is under. So Erdemeister introduced 3 types of moves, local moves, drawn here. They call it Erdemeister moves. So this 1, 2, and 3, you can do in one direction as in your direction. So you get a loop, you have overcrossings of 2 arcs or overcrossings of 3 arcs. This is called Erdemeister moves, and he proved the theorem that 2 nodes are ambient isotopic if and only if you can start from diagram of one and arrive to diagram to another one by a finite number of steps, where each step is one of randomized move or planar isotopy. It gives a possibility to construct a lot of invariants, just considering diagrams. So this is for nodes, and for spatial graph, we have generalization of this result. It was proved independently by Kaufman and Yamada, more or less the same time. So we need more moves because we have a vertices of the graph. And there are moves 4, 5, and 6. And move 4 is clear. You just move a line through the vertex. And 5 is you just use a full twist. And the 6th move is very specific. So sometimes we admit this move, sometimes not. It's 6 moves means we can change order of edges in the vertex. So people distinguish two possibilities: playable vertices or rigid vertices. So if we don't consider such move, we have embedded. If you consider this move, we have embedded isotopy equivalence. If we don't have this move, so we have so-called rigid vertex isotopy. So vertex of our graphs can be considered as ordered, locally ordered, or just you can consider locally plain picture. So all the things get to some disk. So we have such kind of equivalence for diagrams. And now I want to tell about some examples which related to complete graphs. So very nice paper was written by John Conway and Cameron Gordon. It was published in 1983, and they proved this is the following result. If your graph is big enough, for example, if it's complete graph with 6 vertices, so in any embedding, there is a couple of cycles which show a two-component link. And moreover, if you have a complete graph on 7 vertices, so it's always contain a cycle which is given non-trivial node. And this is just very simple picture. If you consider such kind of diagram, so it's you among all cycles, you can find 2 cycles which are linked for black and red. Of course, this is not a proof, just an example. So they prove this result, and this is kind of beginning of the spatial graph theory in mathematical sense, because people started to use some kind of invariants, linking numbers, and so on and so on. And there was many papers after that original paper about graphs in big complete graphs and nodes in these graphs. And the next step was done by Shimabara, who considered bipartite complete graphs. So it's very famous K-free Karotovsky graphs, and Shimabara considered the bigger one, 4, and 5, and he proved very similar results, similar to Conway and Gordon. So in case K44, you have a pair of cycles which give you non-trivial link. In the case of 5, you always can find a cycle which has a non-trivial node. So this is the reference to his paper. And there are different cycles in the graph, and sometimes it's reasonable to consider Hamiltonian cycles. So you have a graph, and you consider a cycle which passes through all vertices. And again, you can ask about noting property of such Hamiltonian cycle. And for complete graphs with big number of vertices, the equation was considered by Foisy and his co-authors, and they proved if your graph is big enough, so it has at least 7 vertices, is again the complete graph. So it's always contain a noted Hamiltonian cycle. So it's a cycle which passes through all vertices and it's given non-trivial node. And after that, we considered a situation with links. So let us define a couple of cycles, a Hamiltonian pair of cycles, which together they pass through all vertices. With my student Andrei Vesnin, so we prove the following result. If you have a graph which is at least K7, so there is always a linked Hamiltonian pair of cycles. So again, this is just example for imagination. So we have K7, and this very particular diagram. This diagram you can find two cycles which give you a linked component. So all these methods they based on technique of calculation of linking numbers of cycles. So sometimes it's possible to prove. And after that, there are also some extension of this approach. So people consider a couple of cycles of given length. So we call it a Hamiltonian PQ pair. If one cycle is length P, another of length Q, and again, people proved just recently this Merishit and Nikuni, they proved that for any P and Q, of course starting from free, because you want to have a cycle in the space, there is in each embedding of complete graph on PQ plus Q vertices, there is a linked Hamiltonian pair of cycles where one is of length P and another of length Q. And this maybe the most new results obtained for couple of cycles. And of course, people consider it more complicated situation, so considered free component links. And I mentioned about some results in this direction. So since we have more components, so we call a graph intrinsically free linked if any spatial embedding has a non-split free component link. And there are some results by Flapan and Pomerenke who studied big enough graph, so complete graph is 10 vertices. We have many vertices because for each component, for each link, we have at least 3, so we have at least 9, but for 10 we can prove. For 10, they prove that any embedding contains a non-trivial or non-splittable 3-component link. And it's not true for complete graph with 9 vertices. And after that, there were some papers where people consider a situation when we remove edges or you remove some vertices. So it's particular two last theorem about removing of 4 edges instead to a common vertex, or removing 2 non-incident edges. So some moves or graphs on graphs we also studied, and we have results in this direction. Of course, people also consider it non-complete graphs, but there are just few results. Mostly people consider complete graph, and for big link, you need a big number of vertices. And I want to discuss mostly graph K4. So it's complete graph on 4 vertices. So there are no information about this K4. There are no results similar to Conway and Gordon. So we have results similar to Conway-Gordon theorem only for n starting 5, 6, but not for 4. So it's some kind of a boundary case, and the last part of my talk will be devoted mostly to this graph. So you can see the graph K4, complete graph with 4 vertices. And for this graph, it's easy to enumerate all cycles. There are 7 cycles, and all these cycles give us the nodes in the space. So again, similar to theta-graph, now we consider a family of constituent nodes. There are 7, and there is a result proved by Yamamoto. So for any 7 can you hear me? There is a special embedding of K4 where all cycles will be realized as these nodes. And also he has remarked in his papers, so there is a known very similar claim of the theorem to for K5 or K6. It's known as true or not. So we have these 7 graphs, 7 nodes, and similar to the case of theta-graph, these 7 nodes, they don't determine the graph uniquely. So what we can say about this graph? And also people started to tabulate this graph. So this kind of initial list of diagrams. You can see there are 4 vertices and 6 edges, and sometimes they form nodes, sometimes trivial nodes. It's this list from Simon, is the very old one. And how we can distinguish graphs? We can use some polynomial invariants, and the most famous is a polynomial suggested by Seiji Yamada. And I want to tell about this invariant. And again, philosophy came from the knot theory, because in the knot theory, we have very nice approach via state sum or Boltzmann sum, which was developed by Luke Kaufman. And to be true, originally this approach was suggested by John Lissing in the beginning of, in the middle of 19th century. So there is a very nice book of Lissing called it Research in Topology. It was published in Göttingen about 1848. And there is a chapter where he suggests such kind of labeling of a diagram, but he also constructs some polynomial, but he goes in the wrong direction. But nevertheless, his labeling also sometimes call it Lissing labeling. So what we have? Suppose we have a diagram of a node, and we have crossing. So we have a crossing, and we can put labels in angles corresponding to this crossing. I mean, we have 4 regions incident to crossing. So we put labels A and B. We have some kind of rule. If you go, so there are overcrossing and undercrossing. If you go in the direction of overcrossing, so suppose the region which is on right is A region on left is a B region. So it's correctly define your labeling, local labeling of this crossing. And after that, you can use a split. So sometimes people call it A channel and B channel. So you just remove this crossing and you obtain more more diagrams. So from one diagram you get it to new, and but with less number of crossings. And example, can you hear? It demonstrates how you can put labeling. So this diagram of trefoil, and there is local labeling in angles or in crossings, A and B, and you have 2 kinds of smoothing, A and B. So if you have n crossings, you have 2 degree n possibilities. So from this one labeled diagram, you can obtain 8 new one. People call it states, similar to Boltzmann states in statistical physics. And each state is just the following. You have a collection of curves, non-intersecting curve on the plane. And Kaufman suggested the following construction of his bracket polynomial, bracket just because of notation. So you consider the sum of all states, and for each state you collect the following information. You count how many A smoothing you use it and how many B smoothing you use it. This AC and BC. So you take variable A in degree AC and variable B in degree BC, and take some D, and you consider D in degree number of connected components on the curves, or collection of curves on the plane. So you construct such kind of sum, and after that you check when your expression is invariant under the randomized move. You say have some relation between A, B, and D, and you can construct invariant, call it a Kaufman bracket polynomial, and if you correct it a little bit, you'll get a Jones polynomial. So this idea, so you have such crossings, you have 2 possibilities for smoothing. After that, you get a state, and for each state, you just count number of components. And very similar you can do for graphs. More exactly, you do the following. So you have a crossings, and now you have 3 types of smoothing. So this it's denoted in the Yamada paper as plus, as minus, and then 0. So 2 just And the third one, we just create a new vertex. So if you take all this smoothing, so if you have n crossings, you will get 3 degree n states, and each state will be just a graph on the plane. And similar to bracket polynomial, we want to construct kind of Boltzmann sum. So we need to keep some information which are obtained. And Yamada suggested to use some kind of graph invariant. So suppose we have a graph with the v vertices and e edges. And let's consider the following polynomial denoted by h. So this polynomial h is a Laurent polynomial of graph G. This is just usual graph. It's no any embedding, just abstract or combinatorial graph. And we can subsets of a set of edges. So and we get an expression which depends on variable a. So for each of states, we calculate this now, this polynomial. And after that, you just take a sum. So what we do is the following. So we consider all possible smoothing in crossings of special graphs. So totally we have 3 degree n states. And parameter m1, just remember how many s plus smoothing we use. M2, just how many s minus smoothing. And if we construct such kind of state sum, which is similar to construction of the Kaufman bracket polynomial. And surprising, maybe not surprising, this polynomial is very strong, and now it is one of the best for understanding special graphs. And Yamada proved the following result. It was published in Journal Graph Theory. So I skip some details from graph theory, but he uses this language. So what he obtained? He obtained the following result. So suppose you have 2 diagrams, and these diagrams correspond to special graphs. So the two diagrams or 2 graphs are rigid vertex equivalent. So we don't use the move number 6. If the equivalent, then corresponding the Yamada polynomials are equal up to some multiplier minus in degree sum k. It's similar to Alexander polynomial knot theory when we consider invariant up to some multiplier. And if you're interested in, so if you consider diagrams of special graphs and maximal degree of vertex is 3, so this Yamada polynomial, this ambient equivalent polynomial up to some multiplier. So our K4 is free valence, so it's you can consider everything up to ambient isotopy here. And very nice property, which similar to many polynomials from knot theory. First property is kind of scaling relation. So if you have four diagrams which are local shown here, so there is a relation between these polynomials. And second rule, just typical move for graphs. So suppose you have an H in your graph, so you can do 2 things. You can remove this H, or you can contract this H. And item 2 describe how the behavior of Yamada polynomial for this. Third one, just normalization. What will give you property is a mirror image property. Okay. It's okay? Because I asked. Okay, so you can consider chirality property. So if you consider a mirror image, so you have the same, but you change variable to inverse, is property similar to the property of Jones polynomial in the knot theory. So you have this Yamada polynomial, and this table how it looks is Laurent polynomial in variable a. So this polynomial is calculated many years ago with my colleague Andrei Vesnin, and if you remember the theory of Jones polynomial, so there's a very important property. We can estimate the span of the Jones polynomial in terms of number of crossings. And here you have similar kind of result. So we have a polynomial, so we consider the span, so difference between maximal degree and minimal degree. And the span of Yamada polynomial was bounded in two ways, different approaches by different groups. So there is a result by Matahashi, Akiyama, and Taniyama. So they estimated span in the following terms. So beta here is just first Betti number, and C is number of crossings in the diagram. And with my colleague Andrei Vesnin, we considered a regular graph. So graph when number of edges incident to vertices is always the same. So 3 regular, 4 regular, and so on. And we obtained result in this language using regularity of graph. And the second proposition about this bound. And if there are no crossings, if there is a usual graph, a combinatorial graph, so equality. So it's many steps we did very similar to development of theory of invariance of nodes. And also another property of Yamada polynomial, the property about of zeros. So jointly with my colleagues from Dalan, from Maureen Lee, Finley Lee, we proved the following result. So suppose we have a family of all special graphs, so we can calculate Yamada polynomial. So what we can say about zeros, and we proved that the set of zeros is dense with a complex plane, and the proof is constructive. So we just constructed a 3-parameter family of graphs, such as the roots of their Yamada polynomial are dense with a complex plane. And I remember I talked about this result in previous conference devoted to Viktor Matveevich 5 years ago. Okay, and of course, similar to the knot theory, people, also the theory of spatial graphs, people try to construct many invariants, and also similar to the knot theory, finally people recognized that the invariants are the same. And it was a story with some invariants constructed by Yoshinaga. So Yoshinaga introduced some else invariant of spatial graphs, and we recognize that this is the same as the Yamada polynomial up to some substitution. And now I would like to discuss the relation between Yamada polynomial and Jones polynomial of associated links. So as I told you, we are interested in K4. It's not so big graph, and we have 7 nodes which correspond to K4, and these 7 nodes can be arbitrary, and moreover they don't determine the graph embedded. So we want to understand what kind of relation between Jones polynomial of nodes and Yamada polynomial of spatial graph. And just because of some technical reasons, we prefer to play with another polynomial invariant suggested by Jaeger, and he considered as a construction of invariant of graphs, of spatial graphs, and it is kind of version of Yamada polynomial if you are working with planar graphs. So this is lemma proved by who last year. It was a preprint. I'm not sure it's published already in some journal, but you can find it in archive. So there is the Jaeger polynomial denoted here by J, and you have a graph with the V vertices and E edges, and you have a special embedding, and you have a diagram of this embedding. So relation between Jaeger polynomial and Yamada polynomial presented here. So it's just you change a variable and you have a multiply which depends on combinatorial structure of the graph. So I want to discuss the case where our graph is K4. So it is planar graph, and you can use this relation as a definition of Jaeger polynomial during this talk. So we have such kind of specialization of Yamada, and what we have. So let's consider K4, and suppose we have a diagram, and let me introduce a notation for ages. So we have 6 ages, and this is just simple picture without noting, but you understand that we consider the diagram, so everything's noted in the space. So we have diagram with some crossings, and we can do the following. We can consider the band diagram. So we consider the little sequence of edges. So you'll get some kind of band diagram in the space, so band surface in the space, and this is kind of band diagram. And topologically, it's just a disk with 3 holes removed. So we have the boundary of the surface. There are four cycles for 4 nodes, and we understand about this boundary component is homologous to some cycles in the graph, so which can be expressed in terms of segments of the graph with suitable orientation. So let's start from a band of the graph, and let us consider this kind of band surface. And we have also associated nodes which correspond to cycles, but we already discussed that this information is not enough to reconstruct the graph. So we go in the direction which was suggested by Kaufman, Simon, Walcott, in Zhu. Is this paper which you can see here. They investigated invariants of theta-graphs into other graphs. So other graph is K4 and some more. So what they proved? They proved with some restriction on the graph. So if graph is plane and number of edges is not more than 6, so there exists unique up to ambient isotopy surface with a 0 Seifert form, and the spine is our graph. So again, we have our graph, and we have a band surface, and our graph is a span of this surface, and we have boundary components, and we can consider linking number between these components. So we put sign plus or sign minus depending on how they intersect. So we have 6 edges, and we introduce WIJ. It's just a sum of signs over crossings of I and AJ, which are edges in our graph. So we can construct Seifert metrics which correspond to linking of boundary components. And the theorem proved by Kaufman and co-authors is that there exists unique up-to-ambient isotopy surface such that Seifert form is 0. So how to obtain this form? We do the following. So we have our surface, and we use additional twists to change sign, to change linking numbers. So we arrive to such kind of system of equations. So we are looking in integers n1 and 6 to correct our surface, where we know W as a parameter which came from our band construction. And we can find, so we can see from the system that this has a solution, and we can find this n1 and 6, and we modify our band surface in the following way. So we have 6 pairs of edges which correspond to edges of our K4, and we use n1 full half twist and 2 full half twists, and so on corresponding paths. So half twist with sorry, not half twist, with full twist. We do this half twist in direction depending on the sign of n. So we do it in a positive direction or negative direction. When we do such twist, so the linking number change, Seifert matrix change, and finally we arrive to 0. So this surface will be uniquely defined. starting from our special graph. So it is called associated surface, so surface associated to our graph. And now what we have in the space, so we have surface in the space, and we have 4 boundary components. So we have a link with 4 components. So we started with a link with these colored components, and after that we added twists in one another direction if necessary, and we arrived to another link, again still with 4 components. Since we used full twist, number component didn't change, but now we have a zero-sided matrix. And we call it this L, associated link to graph, more exactly to diagram D of our spatial graph. And now we go back to Jaeger polynomial, and since we used many full twists, we normalize a little bit this polynomial. So you consider -1 in degree sum of this number of these full twists, and it was done with my student Olga Oshmarina. We proved this is still an invariant of graph. So this Jaeger is still a little bit normalized, and we obtained the following relation. So what we have a special graph K4. So we have 7 nodes which appear as embedding of cycles of this graph, and also we have 6 theta-graphs, which are subgraphs of our graph. But also when we consider embedding of the whole graph, we get embedding of these theta-graphs. So we have the original special graph, and we have subnodes and subgraphs, and everything is 3-dimensional space. So we are interested in polynomial invariants, and the result is the following. So if we consider embedding of K4, and lambda is associated with a link which was obtained from the surface by full twists, and if you consider 7 nodes which correspond to cycles, and 6 theta-graphs which correspond to subgraphs. So it is the following relation. So normalized Jaeger polynomial special graph minus Jones polynomial of this 4-component link is just the sum of this ingredient: 6 theta subgraphs plus 7 node. So the proof is very technical because it needs a lot of calculations, is a simplifying of diagrams, and you see we have the relation between normalized Jaeger polynomial special graph. So this more or less the same as just normalization of Yamada polynomial, and we just Jones polynomial of associated link, and there are some some expression which depend of nodes in subgraphs, and everything will be much more simple if your nodes theta graphs are very simple, for example, trivial. And this is a relation when we have Jaeger normalized polynomial, and of course we can consider this consideration. We can simplify the right part, and finally we arrive to the relation which connects normalized Jaeger polynomial of special graph G, and the following element which correspond to this special embedding. So lambda is just associated link, and there is family of associated link for theta graphs. This denoted by Li. Also, we discussed there are 7 constituent nodes, and we have link which are just parallel versions. So you have a node, and you consider just parallel diagram, you consider parallel line, you have 2-component parallel link. So it's kind of trivial cabling. So totally we have such a relation which relate Yamada polynomial for special graph and Jones polynomial for nodes which correspond to the ingredient of the special. Okay, thank you very much for your attention, and happy birthday to the mathematician.
Any questions, comments? Okay, let's send speaker again. And now put the break and you can start next call 11:20.